So we learned about what are salts. Now we are going to look at the different salt solubility. Okay, why is this important? Is because when you write your chemical equation, you need to put in the state symbol. So for salts which are insoluble, we always write solid. And for salts which are soluble, our state symbol will be aqueous. Okay, and this solubility will affect how we ultimately prepare these salts in the lab moving forward. Okay, so common salts that start with like sodium, potassium, ammonia. This one I always abbreviate it SPA. Okay, so sodium chloride, potassium sulfate, ammonium nitrate. The SPA salt, sodium, potassium, ammonium, they are all soluble. So as long as you see the SPA or group 1 because they form plus positive 1 charge, they are all soluble. Okay, same thing, all nitrates are soluble. Okay, so sometimes you can remember it as SPAN. SPA, sodium, potassium, ammonium plus nitrates are all soluble. Okay, chlorides coming from your hydrochloric acid. All are soluble except 2 of them within the syllabus. So silver chloride and lead 2 chloride. Okay, silver lead, can remember it AP or student needed silver and lead, whichever is easier for you. Okay, sulfates. The sulfates come from your sulfuric acid, and same thing, all are soluble except the lead, barium, calcium. Okay, we remember it as peanut butter cat, or find other ways to help you remember it easily. So peanut butter cat sulfates are insoluble. Okay, when they are insoluble, these 5 that's highlighted in green, we always write solid. Okay, carbonates, not carbonates, carbonates. Carbonates, these are usually found in rocks, naturally occurring. Okay, so they are all insoluble. Rocks are insoluble, except the SPA. So this one ties back into the first part that we learned. Okay, lead 2 compounds, they are all insoluble, except the nitrate. The same thing ties in with the second one. And then this hydroxides, apart from hydroxides, let's write it in, oxides as well. Okay, oxides and hydroxides, oxides is your O2 minus. Oxides and hydroxides, by now you have to know they are bases and they are insoluble. Okay, oxides and hydroxides are all bases and they are insoluble, again except the sodium, potassium, ammonium. Okay, same thing, these are solid. Your carbonate also solid. Okay, the rest which are soluble, state symbol, please remember, we write them as aqueous. Okay, so bearing this in mind, we have to see how do we prepare salts. Okay, salt preparation, the first thing you must ask yourself is this salt that I'm trying to prepare soluble or not? So in an example, NaCl. Okay, sodium chloride, sodium, potassium, ammonium, soluble. So this is an aqueous salt. So if the salt is soluble, come to this way. Okay, are the starting materials soluble? So remember, this is a salt. I can pick the starting material. This second part must come from the acid. The front part will come from your reactions, metal plus acid, so sodium plus acid. Sodium, the oxide, and hydroxide plus acid. So oxide, hydroxide, this is your base and alkali, or your sodium carbonate. Carbonates plus acid give you salt, carbon dioxide, and water. So all these plus the HCl will give me the salt, sodium chloride. Okay, so let's look at their solubility. Metal, of course, is not soluble. Sodium oxide, just now I tell you, oxides and hydroxides, they are bases, right? Natural state solid. Sodium hydroxide, this one you should know is alkali. And carbonate, because it's a rock, is solid. Okay, so your starting material, solid, then I have something aqueous. Since you can use something that's aqueous, let's come to here. Yes, it is soluble. So it is soluble, we do titration. Okay, if you're not sure, let's look at the titration videos in the earlier examples. Okay, so we have to do the method titration, meaning to say your starting material, you must choose NaOH plus HCl. Okay, and this is your acid plus alkali titration. Put it in the pipette and burette. Put your indicator, look for color change. Okay, so all group 1 salts, let's see this, all group 1 salts, all group 2 salts, right? Please always use the method titration acid-alkali reaction. Okay, in the next example, we can look at another soluble salt. Example, magnesium nitrate. Okay, all nitrates are soluble, it is aqueous. Okay, so same idea, MgNO3, 2. This part, the nitrate part, must come from my nitric acid, HNO3. Okay, the magnesium will come from metal plus acid, metal oxide plus acid, metal hydroxide plus acid, and your metal carbonate plus acid. All 4 substances are possible reagents, okay, for preparing magnesium nitrate. Okay, so same thing, let's discuss whether they are soluble or not. Magnesium metal solid, oxide and hydroxide are bases and they are solid. How you know? Let's look back at this table. Oxide, hydroxide, all are insoluble. So they are all solid. Carbonates, still a solid because carbonates are rocks. Okay, so in this case, all the starting materials are solid. So what do? You cannot go and put all these solid into your pipette and burette. So we cannot pick titration anymore. Okay, so in this way, is your starting material soluble? No. So what must we do? We must do this reaction in excess. So what does this mean? So in the lab, this is your setup. You have the solid, one of the 4 solids over here, and then you pour in the acid, nitric acid. Okay, so once your reaction starts, the salt, magnesium nitrate, and water will form. So how do you know this liquid? How do you know this liquid, right? It's not the nitric acid, but it is salt and water only, right? The idea over here is you have to add excess solid. Okay, what do we mean by this? So let's write the equation down, yeah? Example, if I take the magnesium oxide plus nitric acid. Okay, in this reaction, you will get magnesium nitrate, salt partner. All nitrates are soluble, plus H2O. Okay, balance out your equation on your own. So in this example, right, once you put in the nitric acid into the beaker, the reaction will start. Okay, but when your reaction starts, right, you could have some nitric acid, or you try to pour in all your nitric acid, right, and you could have a lot of nitric acid. Okay, so at the end of it, right, this is aqueous, this is liquid, nitric acid is aqueous, and they are all colorless. So if I look at the experiment setup, because they are all colorless, I don't know, is there any nitric acid there? Is it just this salt and water only? So how do you know, right, there is no more nitric acid? How do you know there's no more nitric acid? This is when you add excess base. So add the excess solid, right? So instead of I pour in the acid disregardly, right, I must add excess solid. So at the end of your reaction, because there's excess solid, all the acid is being used up, right? So you will not have nitric acid inside, but instead you will have the MgO, the base that you choose. Why? Because it's in excess. Okay, so now you have an aqueous solution, you have water, liquid state both, and you have a solid. So your remaining product, you can filter easily. So you can filter it easily, right? Once you filter it away, then I will be left with magnesium nitrate and water. Magnesium nitrate and water, you can perform crystallization where you heat to saturated solution. Okay, so the important idea over here is the solid that's added in excess will ensure that all acids are used up. So you can filter and crystallize easily. Okay, so remember these four reagents that we see over here, the magnesium, magnesium oxide, magnesium hydroxide, and magnesium carbonate. These four are all solid, right? We never pick the metal, okay, because some metals are unreactive, example copper. Some metals are highly reactive, example sodium. So there will be an explosion when you try to do the reaction. So what shall we do? Pick the base and pick the carbonate. And most importantly, they must be in excess. Why excess? Ensure all your acids are used up, so you can filter and crystallize easily. Okay, in the next video, we are going to look at ionic precipitation, where my salt is not soluble.